Okay, we know how to describe motion, and now we want to explain the cause of different kinds of motion. So the two basic kinds of motion that we've studied, there were certainly more complicated kinds, but we've studied constant velocity and constant acceleration. And acceleration means the velocity is changing, and a change in velocity can be a change in speed, bigger or larger, or a change in direction. And what we learned with projectile motion is that when an object, that there's a relationship between force and acceleration. So an object moving in a parabola, if we ignore air resistance, the velocity in the x direction is always constant because there's no force. So no force being present means no change in velocity. But in the y direction, there's the force of gravity acting straight down. And so it means that the velocity in the y direction changes at a constant rate because of the acceleration. So the formal statement of the relationship between forces in motion and some insight into what forces are captured in Newton's three laws. So I've written there 1, 2, 3. Pause the video and write down what you can remember about the statement of those three laws, and then start the video again. So don't restart the video until you've written down what you're supposed to. So you're back. First law is called the law of inertia. The statement, the formal statement, is usually an object at rest will stay at rest, and an object in motion will stay in motion at a constant speed in a straight line unless a net outside force acts on it. This is called the law of inertia because it describes any object's tendency, inertia, resistance to change, its tendency to resist a change in its state. In other words, an object at rest tends to stay at rest. You need a force to get it to move. And an object in motion tends, unless a force acts, to stay in motion at a constant speed in a straight line. In the real world, we think things slow down, but that's only because there's air resistance and friction in most cases. So if we want to change the state of motion of an object, we need a force because of its inertial tendency to stay at rest or to stay in motion at constant speed at a straight line. If we want to change that, we need a force. And the relationship, the second law describes that relationship, and the second law is usually written down as an equation. So notice it just doesn't say F equals ma. It says the sum of the forces, the sum of the vector forces, equals the mass times the acceleration, which is a vector. So in practical terms, when we have vectors, as we did in projectile motion, we separated the velocity into x and y components, and that means we should separate the forces into x and y components. So a force in the x direction will mean an acceleration in that direction. A force in the y direction will mean an acceleration in that direction. And we see in the case of projectile motion, there is no force in the x direction. And so in the x direction, it maintains a constant speed, and except for the y part, would move in a straight line. In the y direction, there is a force, the force of gravity, and that results in an acceleration in the y direction. And how much acceleration you get, depending, given a force, depends on the mass. So the mass is equivalent to inertia. In other words, the tendency of an object to not change velocity, its inertia, is measured by its mass. So these are really synonymous, or a better way of saying it might be that the mass is the measure of an object's inertia. So the first and second law tell us something about the relationship between forces and motion. The third law tells us something about forces. What are forces? What are these things that when they're applied, they cause an acceleration, which means they cause the velocity to change? So forces arise in the third law is usually described as an action-reaction, and the normal statement of the third law is for every action, there's an equal and opposite reaction. That could be said as for every force, there is an equal and opposite force. And let's look at an example of that. Two people standing on canoes on a lake, and one person goes up to the other person and pushes. So I push on you. But what happens? You move this way, I move that way. So even though I initiate an action, there's an equal and opposite reaction. And ignoring friction, say the water's smooth, and given the same inertia, the same mass, if I push on you, you will move this way at a speed equal to the rate I move that way. It doesn't matter that I do the pushing. The force is equal and opposite. Vice versa, if you push on me, the same thing is going to happen. So the force is always equal and opposite. The mass may not be equal and opposite. If one person is much bigger and heavier, then the acceleration won't be the same. The light person will move faster and the heavier person will move slower. And that will not matter on who does the pushing. Either person doing the pushing, the result will be the same, assuming a frictionless surface. So another way of thinking about the first law is that all forces arise from interactions. In other words, you can't exert a force on yourself. The person in the canoe, unless they push on something, push on the water or push on the air, they can't make themselves move. So in order to have a force, the person in canoe 1, in order to have a force, it has to interact with something. If the person just waves his arms, it's not going to do anything unless he has wings and he's a bird and he waves his arms and he pushes on the air and the air pushes back. So when I push on the person, there's an interaction and the person is pushing back. Not necessarily in an active sense, but I could replace the person by a wall. And if I'm on a canoe or a skateboard or something that has low friction and I push on the wall pushes back. Now, that kind of defies our way of thinking because we don't think of walls as pushing back. But if we look at this person pushing on the wall, we see that the person will still move backwards. In fact, they'll move backwards more. If it's a big, heavy wall, it won't move. If the wall can move, like the person, then the person would move one way and the wall or the person would move the other way. So this tells us something about the nature of forces. And the way I like to think of the third law is that all forces are interactions, and those interactions result in equal and opposite force. One final example is rather than pushing, we could have a force which is a pulling force. And so you have two people pulling on each other, but rather than just grab hands and pull, I'm going to put a rope or a spring. Let's use a spring because a spring stretches, and we know that the more it stretches, the bigger the force. So if person 1 pulls back, the spring will stretch and will exert a force on this person this way, but it will also, since the spring is pulling in both directions, it'll exert a force on the person this way, And if the two people are on skateboards, they will move towards each other. And how will they move towards each other? Well, they will accelerate toward each other at a rate which depends on the inertia or the relative mass of the two people. If they're equal in masses, they'll come toward each other with an equal acceleration because the force exerted is related to the mass and the acceleration. And if we rewrite that, the acceleration that we would get in this case would be, let's call it AX because it's along that direction, would be the net force, in this case the spring force, in the x direction divided by the mass of the object. So you can see from this that the acceleration is proportional to the force, bigger acceleration, but inversely, this is what we mean by inverse relationship, inversely proportional to the mass.